Hello and welcome back to the Energy Onion Energy Systems Engineer Training Certification, Chapter 7. Well, you've been with us now for 6 chapters. We're beginning Chapter 7, the shortest of the Energy Systems Engineering chapters. Some of the content we've looked at greater depth, such as lighting, HVAC, building envelope. And the reason is twofold. One is the exposure that you as a provider or you as a representative of your organization typically will have more exposure to lighting, HVAC, and building envelope, lead, and so forth. The other reason is that these industrial systems, electrical systems, and these chapters later are not technically immature. They're very complicated, and they could be. Some people make 40, 50-year careers out of just one of these chapters. But we at Energy Onion had to look at what we perceive your needs to be and right-sized training. Most people wanted this training to be a day or less, and so we had to decide where to draw the line. And in some of these chapters, we drew the line just below the surface. And this chapter 7 is an example of that. As you consider control systems, you look at what they do. And what they're intended to do is what you would do if you could constantly watch and adjust the knobs on the machine. The control systems are used to regulate equipment or systems or processes to keep them performing near their set points. They're used to coordinate. That involves if you have a sequence of processes or parallel processes, the control system can coordinate the logic amongst those processes in accordance with the requirements. Control systems can automate, but be careful. They will automate whatever they did before. They cannot make judgments or split-second complex decisions with new data. So if you have a process that's not working and you have it automated, it'll not work every time. The next thing a control system offers is consistency. Because of automation, the control system can measure and make changes to obtain consistency in your process. Again, it can't make a judgment call, so if it's making something bad, it'll make it consistently bad. And the last one, this idea of a control system being used for conservation, is really just a summary of the control systems above it. Conservation can be achieved because a control system can regulate, coordinate, automate, and be consistent. An example is, let's say you have 200 offices in an office building. Your control system can monitor outside air temperature and humidity and predict what it will be in the next 6 hours. It can measure indoor temperature and humidity in your 200 office spaces. And it can make the decision whether to be in chilled water mode or economizer mode, a decision you could never make because you couldn't get the data and make the decision fast enough. But the control system can conserve energy by enabling that decision that's otherwise out of reach. Consider, however, the success of a control system. 43% of the control system success is that it's properly implemented. 40% is the intent or the specification, that it's properly specified. And 17% of a control system success is still in the hands of the operator. This list of control strategies is, in essence, what can a control system do? For example, and this list is where you need to spend most of your time understanding these control strategies. Because again, we're not going to bring up control systems programming, but if you're a user of energy, there's a good chance that you will encounter these control strategies. So let's get to the definitions. First is just scheduling. A control system can program a system or equipment to start and stop on a schedule or for holidays. The second one is a control system can offer demand limiting or load shedding. The system can reduce your demand by turning something off or turning something down. The control system can coordinate minimum on or off times. Some systems, once on or once off, need to remain in that state either for efficiency or for equipment lifetime for a certain period of time. And then they can be allowed to be switched to the other state, either off or on. Duty cycling means to change or control the ratio of on period to total cycle time of this on and off controlled equipment. So duty cycling changes that ratio. The idea of optimum start and stop involves tracking heat loss or heat gain during off hours. And alongside of that, tracking outside air temperature. And with that data, determining optimum shutdown and startup to minimize energy. However, doing so while maintaining comfort during business hours. We addressed in a previous chapter that if you make changes and negatively impact the people inside the building, you have cost much more than the energy savings can justify. The next idea of night setback is a very common practice, and it just allows the temperature when people aren't there to set back 6 to 8 degrees. So in the summertime, you let it get 6 to 8 degrees warmer. In the wintertime, you let it get 6 to 8 degrees cooler. And it's often used in conjunction with other control strategies like optimum start-stop. The next four, hot water, chilled water, condenser water, and supply air, are what's called resets. And all the reset strategy is allows something to change as the demand for that thing changes. So hot water reset allows you to vary hot water temperature as the demand for hot water changes. Chilled water reset allows you to change the temperature of chilled water as the demand for chilled water changes, and likewise with condenser water or supply air. Boiler and chiller optimization. Imagine if you had multiple boilers, multiple chillers, and one was much more efficient than the other. Well, aside from having somebody physically go turn one off, your control system can prioritize the most efficient optimization of your boilers and chillers. Next is the economizers, controls strategies for economizers. That was our example of control strategies earlier, telling you or automatically adjusting the system so that when it makes sense for an economizer to be used, the control system uses it. Recirculation is the idea that if your business starts at 8 a.m. and people start coming in at 7:30 a.m., you can't turn the air on at 7:30. It'll still be too hot by the time when people get there. You have to turn the air conditioning on and allow it to cool the building down so that it's at the proper set point when people arrive. So if you start the air conditioner at 6 a.m. so that it'll be cool by 7:30 a.m., you can cool your building down faster if you would shut off outside air, fresh air makeup. You couldn't do it with people in the building, but without people in the building, recirculation says shut down the exhaust and the outside air for a period so that you can cool or heat your building faster. And then, of course, motor speed control. We've talked about that in the electrical systems and motor section. With control strategies in mind, now let's consider control devices. And these terms, again, they're terms that if you understand them, you don't have to mentally check out when your customer or your operation or your facility starts to discuss these. You know what they mean. A transducer, it's used typically to refer to converting some physical phenomenon like temperature into an electrical signal, or converting an electrical signal into some physical phenomena. That's typically how it's used, but technically a transducer is just something that converts one type of energy to another type of energy. A transmitter is a transducer plus a signal conditioner. An example would be converting a signal to 4 to 20 milliamps so that it can be seen as an input by a control system. A switch is a two-position device: on, off, open, closed. Sensors are input devices. An input device that measures some variable of interest. The performance of these control devices is captured through the ideas of accuracy, repeatability, and drift. Accuracy can be reflected or reported in a few different ways. Let's say you have a 100 psi gauge. The accuracy could say it is 0 to 100 plus or minus 5. It could say it is 0 to 100 plus or minus 10% of the reading. So if you read 20 psi, that would be plus or minus that 20, the reading, some percentage of the reading. Or it could say plus or minus some percentage of span. So if it's a 0 to 100 span gauge, maybe 10% of span, then your accuracy would be plus or minus 10. So accuracy is, if it gives you a number, how sure are you of the exact accuracy of that number? Repeatability says, if you take that measurement 10 times, how close will those 10 measurements be together? And drift says, if you take that measurement 10 times over a course of time, maybe 10 days, will that value drift up or down, or neither? So why so short? Well, Energy Onion had to make a decision about what was appropriate. What would we believe would bring you the best value? Certainly there's a tremendous amount of material in building automation control we didn't cover. And it's not because we don't know it. It's because we believe that the best thing for most people who seek this training is to have a conversational ability with building automation and control. We believe that the technical background, the engineering, in this case, unlike something in lighting or in building envelope, in building automation control, the technical background, we believe, will be a hindrance to you. It will unnecessarily complicate your understanding of building automation and control. Certainly, some people will say, well, it's not that hard. Look at this picture. It's just a simple control system. It's not that hard. And even if I showed this system, they could break it down, and they could explain every component and the function. But for most people, this information, this understanding the engineering behind a building automation and control system is not why they're here. It wouldn't help. It would be a hindrance. So therefore, we have chosen to truncate the building automation control with that definition of control strategies and control devices.